In this example, we're asked to integrate x cubed times natural log of x. The thing to notice here when you're getting started is that you've got a product of unrelated functions. We've got a product of two functions where a u substitution is not going to work. One part of this product has nothing to do with the derivative of the other part. So typically if you have a product and you're going to do u substitution, you've got your expression of u times du. So part of this would involve the derivative of the other part. That's not the case. These are unrelated functions. So this is when you would want to use integration by parts. So the formula, when you use integration by parts, says the integral of u times dv is equal to u times v minus the integral of v du. So what this will entail is, first, you take what's given inside your integral, and we need to decide what part of this expression we're going to let u equal and which part we're going to let dv equal. And this first step is the main thing that requires a lot of practice. There are some general guidelines that I've mentioned in the notes, but overall, just it takes practice to get good at selecting u and dv. One thing to keep in mind, though, so we're going to let part of this integral equal u, we'll let part of it equal dv. Whatever you let u equal, we're going to need to find out what du is, which means we're going to take the derivative. So we're going to let u equal part of this, and then we'll use that to find du, which means going from u to du, we're going to take the derivative of whatever we let u equal. So it's nice when you're selecting what you let u equal if u is something that gets simpler when you differentiate. Also, so we're going to let dv equal part of this, part of what's inside this integral. Once we select what dv is equal to, we're going to have to determine what v is equal to. And so when we're going from the part of this integral that we identify as dv, and then figuring out what v is based on that. So going from here to here, we're taking the antiderivative. You're going from the derivative of v back to the original expression v. So over here, we're taking the antiderivative. So we're integrating. So another thing to keep in mind when you're doing integration by parts is you need dv to be something that you know how to integrate. And even further than that, it'd be nice if it's something that we can integrate quickly or integrate easily. You want to avoid letting dv equal something where integrating it, so finding v, is a whole other, complex process. We want to avoid that. Okay, so in this integral, I think I'll use colors here to highlight this. I'm going to focus on the natural log of x. We know the derivative of natural log of x. It's 1 over x. We don't actually at this point know the antiderivative of natural log of x. That's actually never come up. As much as you've used natural log of x, maybe even in your calculus class, we never have integrated the natural log of x. And actually, you use integration by parts to find the antiderivative of natural log of x. I'm going to create another video where I do that. But for now, let me just say, okay, I don't even know the antiderivative of natural log of x right now. So that's definitely not a good idea to make ln of x dv. I should make it u instead. So I'm going to let u equal natural log of x because I know the derivative of natural log of x is 1 over x. Okay. That leaves the x cubed dx is equal to dv, which now taking the antiderivative means that v must be x to the 4th over 4, just power rule for antiderivatives. Now we just apply the formula. So the integral of, here's our u times dv, all of this is dv, is equal to u times v, so u, which is natural log of x, times v, which is x to the 4th over 4, minus the integral of v, which is x to the 4th over 4, times du, which is 1 over x. Before you go any further, so before you do anything drastic with this integral here, like integrate by parts again, make sure you simplify. Always make sure when you apply integration by parts, the integration by parts, I'm calling it a formula here, but so when you apply this process, you make sure that you simplify this integral of v du expression before you decide how to proceed. So to simplify this, I mean, there's a common factor of x here we can cancel, so this will be x cubed. And the 4 in the denominator, I prefer to pull that out front as a constant coefficient. So I'm going to write this as x to the 4th over 4. Just I like to have the logarithm in the back here, times natural log of x, minus, so I'm going to pull out 1/4 from this 4 in the denominator. And I'm left with x cubed times 1, so integral of x cubed over, this x canceled, so it's just over 1 now. And antiderivative of x cubed, so that's straightforward enough here. So I'm writing what I had on the previous step. Minus 1/4 times the integral of x cubed is x to the 4th over 4. Okay, and we could clean this up a little bit. I don't know how much you guys want to. I could factor out x to the 4th over 4. One neat technique is to factor out x to the 4th over 16. You don't have to do it this way, but if I do, let's just think about it. So factor out your least common denominator. If the denominators here are 4 and 16, least common denominator is 16. Which, okay, so if I get a common denominator here, it'd be times 4, top and bottom, right? So now this has 16 in the denominator. So if I factor out x to the 4th over 16, I'm left with, still got this 4 in the numerator, so 4 times ln of x, right? 4 times, I didn't mean for that to be blue, ln of x minus, we factored out x to the 4th over 16, so minus 1 plus c. Okay, this is the pretty way to write your answer, but I would accept this for full credit here. So don't worry so much about this last step. I believe when you're checking answers in the back of the book, they may do this sort of thing a lot, going from here to here, but it's not something that I'm going to insist that you guys do. So it's okay if you leave it in this boxed form here. Might be nice if you at least call this 16 in the denominator.